to the second video in the demo series. In the first video, we created an STK scenario from scratch, inserted a satellite object, and did some initial configuration in SOLIS. In particular, we added mass properties to the spacecraft as well as some initial modes for sun tracking and nadir tracking that we could then do some real-time commanding during runs, as well as added some telemetry to the configuration so we could see some data coming out through STK using the report and graph manager. In this video, we're going to start from that initial configuration with mass and modes set up, and then add on subsystems. In particular, we're going to add on an attitude control subsystem, attitude determination, and power. So far, with just mass and modes configured, we are using perfect control for our attitude control system. This means that any command that is issued, torque or guidance, is being achieved exactly. There's no delay, there's no actual integration of components that are executing our attitude maneuver. Similarly, for attitude determination, the flight software knows exactly its attitude. There are no sensors that are going into a filtered solution for the spacecraft attitude. To get started, the first thing we're going to do is configure some sensors. So if we go to the sensor page, it has a list of available sensor types that we can use. If you click on one, you see a plus at the bottom that appears that you can use to add a sensor manually depending on your spacecraft design. Also, there's a wizard option at the bottom, which we're going to use. There's one on sensors, there's one on actuators, and a few others that help you configure the spacecraft when you don't exactly know what you're designing yet. So we can select the wizard, and it provides us some options. We can pick the type of orbit we're interested in, our typical pointing that we want to issue, as well as our intended sun point and nadir point vectors, and the precision that we want out of the attitude determination system. By default, medium precision is selected, as well as this configuration of sensors. We want 2 horizon sensors, 2 sun vector, an IMU, and a magnetometer. You can change those if you have a particular idea of what your spacecraft might be, but for now we'll leave the defaults. We'll change the target orbit altitude to be 1,000 to coincide with how we configured our scenario. Then all that's left for us is to configure the nadir point vector and the sun point vector. If you remember, we used the near satellite in our configuration as the 3D model because it's nice and symmetric. When we want to do sun pointing, we want the back of these panels pointed at the sun vector. So we want to make sure we have our negative body Z axis configured. So rather than Y, we're going to update that to be negative Z. Then for the nadir point vector, we're going to take a look and we want our positive Z pointing down when we point nadir. And so this is already correct. So this completes our sensor wizard configuration of how we want to generate our sensors, at least initially. And then from there, when your design matures, you can start to update it and reconfigure it. So what exactly did that do for us? That created, as it said it would, 2 horizon sensors, an IMU, a magnetometer, and 2 sun vector sensors. Within each page, for each component, there are configuration parameters specific to the particular sensor, how it's oriented, how it's set up, the various parameters that go with the sensor. In addition, there's an Odyssey simulation truth model page, which will allow you to configure the parameters of the sensor, as well as the noise and some errors that you want to introduce to the system. Once you start to have actual parameters associated with particular components that have been selected, you can come to these pages and update them from the wizard values that were automatically given to you. So this type of page is available for each of the sensors that have been configured. IMU has its typical random walk, initial bias, scale factors that you would add after you have selected a particular IMU and update to reflect the hardware that you're going to use, and the same for magnetometers and sun vector sensors. So with all of those configured, we can now jump back over to the attitude determination system and notice that perfect attitude control or attitude determination is no longer selected. We have a fixed gain filter, and then as part of the configuration for the attitude determination, it has automatically populated the sensors that it created for us. And for each of these sensors, we have an option for if we use it for initialization when the spacecraft flight software boots up. If it's incorporated in the attitude determination system solution, it's either none, attitude and bias, or attitude only. What the residual limit is, as well as a time constant for the particular sensor to help out the attitude determination filters. In this case, we're going to leave the presets and the defaults, no reason to change it at this time, and move on to configuring our actuators. Adding actuators is very similar to adding sensors. Available options are over here on the left tab. You pick one and then hit the plus button to add. However, you'll notice there are two different sections here compared to one for the sensors. There's actuator sets and actuators. The importance comes in when we start to talk about the attitude control system. Actuators that you create are then grouped into actuator sets, and we'll see that in a second. Similar to the sensors, we're going to use the wizard since we don't have a particular design in mind yet. The wizard is going to provide us with a few options. It's going to ask that we configure the mass properties first, which we have. It wants to know that because the primary input for the actuator wizard is what is your desired time for a slew maneuver. That's going to help it determine how big the actuators need to be to meet that requirement that you're providing. So the options for primary attitude actuator are reaction wheels and thrusters. And for momentum actuators are torquers and thrusters. So we will leave the default values in here. We have our mass properties configured, and we will just say create actuators. Now what this has done for us has created X, Y, and Z reaction wheels with appropriately sized values to meet the time requirements that we gave it in the wizard, as well as magnetic torquers for X, Y, and Z axes. Options for this look similar to for sensors. For the spacecraft configuration itself, it's the mounting, and as well as the mass properties of the actuator that was configured. And then for Odyssey, more model-specific parameters that you can provide, such as friction, inertial wheel speed, quantized wheel speed, things where you can start to hone in on the actual design of the actuator once you get a better idea of the component you're going to select. So the same exists for the magnetic torquers, the truth and how it's configured on the vehicle, as well as model simulation inputs such as alignment error. If we take a look at the sets, what this has done is automatically create a reaction wheel set and a magnetic torquer set, and it's added our X, Y, and Z reaction wheels to this set. The set is what gets input to the attitude control system, which we'll see in a second, and it allows you to separate wheels if you have more than 3 or even 3 that you want to separate into different sets and configure them on different axes for the control system. You can do that. You can also enable and disable particular actuators within a set and have just a higher level of control over how you configure your spacecraft depending on any unique need. So now if we jump over to the attitude control system, we're still on perfect control. What we want to do is update this to PIID control, and we can actually start to configure the attitude control system. So the default control algorithm has been configured with these unity gains mostly. You're using a PIID control system. So our input that it needs is what actuator set are we associating with each control axis for both the attitude control and the momentum control. So for attitude control, we're going to select our reaction wheel set. And for momentum control, we're going to select the magnetic torquer set. So this is all the system needs to now make the connections for the real flight software that's running in the background, saying the attitude control system is now going to be connected and configured to use the reaction wheel sets for the attitude control and the magnetic torquer sets for the momentum control. At this point, we have a completely configured attitude control system and attitude determination system with sensors and actuators. So all of these will get instantiated and configured for use within the Max Flight software that runs in the background. And that is going to allow us to now do a run and use an attitude control system and issue commands and have it spin reaction wheels and actually start to propagate the attitude dynamics within the Odyssey simulation. Before we do that, we're going to jump over to the telemetry interface. We've added some new components, so we want to make sure that telemetry is coming out. So we have this actuator processing that's new that we're going to add actuator sets, as well as the Odyssey actuator model. Once those are added, we'll say OK, and we can start a new run. What this is going to do at first is allow us to generate some data for those new telemetry packets that we just selected within STK user supplied data. So before we issue some real-time commands, we're going to jump over to the report and graph manager, bring that up, and we have this predefined actuators that we'll take a look at for plots. Remember, SOLIS is communicating data through user supplied data. back to STK. So if we filter on user supplied data, we'll see our now actuator processing, actuator sets, and this actuator model within Odyssey. We've pre-selected the X, Y, and Z filter speed coming out of actuator processing for the flight software. So we'll say, okay, we're happy with that. Switch to our dynamic display plot and bring up this actuator plot. Now, we'd like to get these both running on the same axis. So we're going to go back to SOLIS, stop our run, reset, change some windows up here so that we can start to see things a little easier. Restart our run, tile our windows. So now this is running. These are on the same timeline. So we can see our attitude and our oiler angles, and we can see our reaction wheel speeds, which are all 0, because we haven't done anything yet. So we'll jump over to real-time commanding, go down to our mode control, and issue a tracking command. First, we can do a nadir track, prepare and execute that command, and immediately we see the reaction wheel speeds jump up, and actually Odyssey is running these reaction wheel models based on attitude commands that are being issued by the real max flight software that's running in the background. One thing you'll start to notice here, though, is we're not in particular control of the attitude. So we are going through and trying to hit this nadir command, but we're not achieving it. We have an unstable attitude control system. Our attitude is all over the place. So what happened? So we'll stop this simulation and jump back over to SOLIS and take a look at our attitude control system page and notice that we left all our gains at Unity or whatever their default value was. What we failed to do was tune this control system to actually control the spacecraft that we've configured so far. Up here in the upper right is a run attitude control wizard that can do that for us. So the primary input here being the controller bandwidth, how fast do we want to be able to respond to commands? So we'll take the default and up it to 0.1 hertz. And what that's doing is showing us some gains that it's generating primarily based on the mass properties of the spacecraft, the mass properties of the actuators we have to tune the controller for what we've configured so far. So we'll say generate gains. Okay, and that's going to populate these values for us with a stable control system for our spacecraft. So we accept all changes, then come back over here, reset, and run our simulation again. Once that starts, we can reissue our nadir track, and this time we should see the spacecraft respond. Here's our reaction wheels responding, spinning up to change the orientation of our satellite. However, we should be in control and come to rest at this nadir vector and see the reaction wheels speed come down and rest at a value of whatever is required to keep the spacecraft in this orientation that we've requested. So as expected, we see our attitude change, we see the reaction wheel speeds go up and come back down, and now they're settling out into this steady state position. We can repeat that process for SunTrack, and as we issue the command, we see the reaction wheel speeds respond, and correspondingly the spacecraft attitude respond. And remember, this is running max flight software in the background. We are issuing these commands to max flight software, which is executing a real control algorithm that would execute on a spacecraft, and Odyssey that is running within max is simulating the 6 degree of freedom dynamics models to propagate the attitude based on the spacecraft mast and the reaction wheel speeds that are being commanded. At this point, we have a completely configured attitude determination and control systems along with the sensors and actuators that go into that system. Now we'll turn our attention to the power modeling. If we reopen SOLIS, take a look at the left, there's a power thermal page that we want to navigate to. Under this page, there are 3 main tabs, the power, batteries, and panels. We'll come back to the power tab. First, we're going to add a battery to our spacecraft. So we just hit the plus button and it's going to provide some default values here, which we will leave. As you refine your design and get more of an idea of what the battery will look like that you're going to use on your spacecraft, you can provide actual charge and discharge voltage curves here through this table input. For now, we'll leave the default. Moving over to panels, we want to add panels that are on our spacecraft and have solar cells. And so we have one in the positive X direction and the negative X direction, as well as positive Y and negative Y. and we want to add solar cells on the front and back of these panels. So coming back over to the panel page, we're going to hit a plus, and the first panel we'll add is a panel in the X positive direction. Taking a look at the panel, let's say it's 1 meter by 2 meter, and so we have a 2 square meter surface area. For the surface normal, we have, for the front side, let's say it's facing down in the positive Z direction. So we want to replace this X vector with a positive Z vector for the unit normal for the body. And then what we also want to do is provide include backside, because we're going to put cells on both sides of these panels. When we do that, it's going to provide to us already the correct unit vector for the direction of the panel that's on the back. And the last thing we want to take a look at is the solar cell type. So we've made our panel, but we don't have any solar cells. So right now we don't have any configured at all to select. So let's accept our change and jump back to the power page, which is going to provide us an ability to define solar cell types. So let's hit the plus button, and it's going to provide us a default solar cell type that we can rename and adjust the efficiency for. We'll accept the defaults and say OK, and jump back over to the Panels tab, which will now have our new solar cell type as an option that we can select for both the front and the back on our spacecraft. It also provides us the option to change the area fraction. So say all 2 square meters of the front side of the panels isn't actually covered in solar cells, and instead of 0.9, we'll say it's 75% and leave the back at 0.9 and say OK. You'll notice that we haven't actually told SOLIS where the panels are relative to the main body. At this point, it's not required. The surface area in the unit normal is enough to calculate the orientation relative to the sun to get the incidence angle for the power model. If we were to start to include some environmental disturbances, such as aerodynamic drag or solar force, we need to specify where the panels are and how they're oriented. So that's where this comes in, where we provide a panel origin as well as the center of pressure location so that you can do accurate force calculations and moments that are coming from the panels. But for the purposes of this demo, we're going to ignore those environmental disturbances and say we have completely configured our panel. So now we only have an X positive panel. We need to copy this for the other 3 that exist on our spacecraft. So we'll just use this copy button to copy it 3 times and rename our panels. So we now need an X negative direction and say OK. So it maintained our solar cells, maintained our surface area. So we'll hop over here and now rename this to be a Y positive. And then similarly, rename this last one to be a Y negative and hit OK. So now we've configured all 4 of our panels with the correct surface area and unit normal for the front and back, and put solar cells on both sides of the panels. So at this point, we can now rerun and take a look at some power properties that are being modeled within SOLIS and STK. But before we do that, we want to take one more look at the STK telemetry interface and add telemetry for the components we just added. So under power and thermal, we now have battery and panel power. So we will just go ahead and re-add that packet and accept changes. So at this point, we can now run and get that data back into STK and take a look through the report and graph manager. So we will close this, reset our simulation, and rerun. So as it starts to rerun, we can now get the new telemetry data into our report and graph manager. So we will reopen that and take a look at this pre-configured battery. In here we have the generated load as well as the generated power by the model that is living within Odyssey, the power thermal model. If we click on these, we can take a look at, again, it's coming through user supplied data in this now Odyssey power thermal section. So we'll say OK. And then we want to generate that as a dynamic display. So that'll bring up our generated power, our load power, and our battery state of charge percentage. So we can minimize our report and graph manager And we'll go ahead and stop this simulation and reset it to get these two plots on the same axis view. So then we restart our run, say OK, and we can start to see what our generated power and our battery state of charge does as we start to command the spacecraft. So we can go to our slew to tracking, issue, let's say, a sun track, and we see our reaction wheels start to spin, our attitudes start to change, our generated power is now changing as the orientation of our panels change with respect to the sun. Our state of charge is changing as the battery starts to charge. However, we are seeing that the load power is not changing, because that's one thing we didn't do when we set up our battery model. So if we go back to SOLIS and take a look at our power thermal page, we didn't go in on this power tab and add variable loads. So let's go back and do that. So we'll add payloads, communications. We know we have reaction wheels and magnetic torquers. We'll say OK. And so now when we stop and restart, we should be able to see these things affect the load that is in the power model on the battery. So we'll go back to our run window, stop and restart our simulation. Run 5 times real time. Let that start up. We'll go back to our slew to tracking, issue a nadir track this time, prepare and execute the command. So now, as the reaction wheels spin up to execute that maneuver, we start to see the load change on the battery, which is what we expected. So now we can start to see, based on the reaction wheels we've selected and what the load is that they're going to pull from the battery, we can see how it's affecting the total load on the battery and the state of charge of the battery. So as these reaction wheels start to spin down and we complete our maneuver, the load goes back to whatever value it is for the reaction wheels to keep the attitude that we've requested. So if we do that one more time, we can see it as it does a sun track. And once again, our wheels spin up and we see the load on our battery change over time, as well as the generated power and the load on the battery overall, and our attitude updating. So at this point, we have completely configured the attitude determination and control system, as well as a preliminary power model to start actually modeling the subsystems in our spacecraft. Next time, we're going to start to take a look at the sequencing so that we can leverage the powerful sequence engine that lives within the Max Flight software and start to actually schedule and command sequences rather than having to issue these commands by hand as we're going through our spacecraft maneuvers.